All right, guys, here we go. So, average range is 2.3. It's normal. This is the key thing to look for. Yep. All right. Otherwise, you can't do it. If I didn't say that, you can legitimately say, I can't do shit and turn it in. You probably should instead say, I think you meant to say it was normal and then do it, because I'm not going to just make a whole quiz that's like, let's see if they get the trick. No. So don't assume I did that. So less than 770. So I want to draw the picture for myself. In the middle goes what? I like it. And I want an exposure less than 770. So that will go down here. By the way, if you fly a lot, your average exposure is higher than average. Because when you get up higher above some of the atmosphere, you're getting hit by a lot more radiation. Unfortunately, you don't develop powers, so don't look for that. So now, what do I want to do with the 770?
Find the Z-score.
Make it to a Z-score. So they gave me a raw score. And when I say a raw score, I mean something with units, minutes, inches, whatever. I want to convert that to a standardized Z-score. And this is the part that I don't know if students ever get this. I don't care what the mean was or the standard deviation was. The minute I make it to a Z-score, a Z of 1 has the same area below it. But real quick, go with me. If the mean was 40 and the standard deviation was 10, what would a Z-score of 1 mean? The mean was 40 and the standard deviation was 10. Say again, you said? Read the wrong way. 50, right? 40 plus 1 step is 50. If the mean was 40, but the standard deviation was 200, what would a Z-score of 1 mean? 240. So it would be more spread out if I drew it with the normal units, but the minute I make it a Z-score, the areas always kind of follow the same pattern. Right? So it always has this bell shape. If it's normally distributed, it has this bell shape. If I make everything Z-scores, oh my goodness, make everything Z-scores, then they always have the same areas. All right, maybe. So let's see, this Z-score is 0. What do you guys get for Z-score 770? 0.26? 0.23? And then, now that's a Z-score. So notice what I did. When I took statistics, we had to draw like a second picture underneath. What first picture was for raw scores. So I'm like, what the hell did... In parentheses, you could put the Z-scores. Right? Be nice to yourself. Identify what the hell it is that you just found. Be nice to yourself. Some people just tell me the answer is 23%. That's no good. That's a Z-score. Then what do you get when you look it up in the chart?
5910.
I like it. 0.5910. And that's done. You're done. How do you know you're done? How would the question have said? What would it have said if I had to do 1 minus? What would the question? What would it be different? More than. Instead of less than, it would ask me more than. That's it. The chart tells me the area below a Z-score. So if the question is all about less than something, I look it up. Once I get to Z, I'm done. I don't have to do 1 minus anything. All right, how are we feeling? Great. So you see how everything is relatively easy if I know I have a normal distribution. So a big part of statistics is, all right, when can I say it's normal enough to use the chart? So we're going to have different, like a binomial looks sort of normal. I don't know if you remember that. I gave you that with the heads, flipping a coin 14 times, the handout. Remember the handout? And they had this big histogram in the middle, looked kind of normal. So there's a test for binomial, and we can actually see, is it normally enough? And then I can just use this chart for probabilities. What? Cool. All right, so this guy, same idea. 718.3 in the middle. 860 way up here. I want probably greater than 860, right? This is probably like an airline pilot or somebody. Probably even more than that. So again, I make this into a z-score. What was it? 223.56. Just to show you the formula for once. So that should have been what your formula looked like. Hopefully your numbers look differently than mine. You can write better than me. That would probably be better for you in life. And then, I'm sorry, do it again.
0.6.
0.63. Again, people, be nice to yourself. Remind yourself that's a z-score. Don't say 1 minus 0.63. That wouldn't make a damn bit of sense. Now I'm just changing where I am on the picture. That's a z-score. What do I need to find out?
Probability.
The area, the probability. So 0.63, I get 7357. Where does that go on the picture?
To the left.
7357. So what's this area going to be?
1 minus.
Yeah, 1 minus this. So make it 9, 2, make it 9, 6, make it 9, 4, make it 10, 3, 2, 6, 4. Now some of you guys, I don't know if anybody's using the shortcut. You could have looked up negative 0.63 and got 0.2643 immediately because of the symmetry. If you don't have a clue what I just said, don't worry about it. It doesn't really save you that much time, right? It's because of symmetry. Alright. So I like how every time I draw it's very different. So just showing you all the possible ways you can look. 718.3 again in the middle. I want between 60 and 400. I'm not going to take points off for your scale being inconsistent. This is just a quick visual aid. But make sure that everything's on the correct side of the mean. Right? And then on the correct side of each other. That always helps. Now when I convert everything into a z-score, well that's 0, that's nothing else. What'd you guys get for the z-score for 60?
Minus 1.4.
I think that's for 400, right?
Oh yeah, sorry. Minus 2.9.
294?
94.
What about the 400?
Minus 1.4.
42?
Yeah.
1.42?
Yes.
Yes, Jeff. Okay. So those are my z-scores. I just put them in parentheses so I know what they are. Now if I look up negative 1.42, that won't be my answer. It's too much. What do you get when you look up negative 1.42? 0778? 0778. And when you look up negative 2.94?
0.0016.
0016, I like that. Stereo. And then you just subtract those to get the area between. Is everybody doing okay? Trust me, if you're not, there's at least 8 people in here that aren't also. So I don't know how important I can make this sound. I need you to realize this is going to rule our life for a little while. The more you understand this is what I'm going to call the easy z-score problem. Is this. Because it will get a little more complicated. You know it's going to happen. So here where do you get 0.077a minus 0.0016 is 0.0762. So what's that mean exactly? Give me a couple different ways to look at that. I like it. The direct way to look at it is to say the probability of good. Probably of a person being chosen that has an exposure level between 60 and 400 is 7.62%. A slightly more practical way to say it is 7.62% of the population has an exposure between 60 and 400. That sounds more... That's sort of like my little brother. I can't believe I didn't tell you about my little brother. He always gives me shit about teaching probability because he says, Jeff, it's all a scam, man. Everything's 50% chance. It's either going to happen or it ain't. I was like, all right, thank God you didn't become a doctor, Jim. You know, what's my chances, Doc? 50-50. So, I love my little brother. He's like, did you tell my story again? I'm like, yes, I did. Do you still believe that way? Yes, I do. I'm like, all right, whatever. Hopefully, you guys understand the usefulness of probability. It can't tell you exactly what to do when, but it tells you what to do that'll have the highest chances of succeeding. Right? I mean, that's what we want. So that's a more practical way to interpret the answer to one of these kind of problems. And remember, it kind of makes sense. If 11% of you guys are left-handed, what's the probability I pick a left-handed person at random? 11%. So if the probability of picking somebody 7.62% that does all that, then 7.62% of the population does that, right? So it's a better kind of way to interpret that answer. Blah, blah, blah. Okay, what about part D? How do I draw that? Like that. Okay, where do I put 2%?
To the right.
Yeah, it's the top 2%, so it's got to be this little 0.02 there. It's a percentage, so it's an area. So what's below that? 0.98. I need that so I can use this little dude. 0.98, the closest you can get. Let's see who got it right. Yeah, 9798. It's a little bit closer than 9803. That's 3 away, that's only 2 away. So 2.05 is your z-score. Now, is that my answer?
No.
I want the level. So I need this number here that's missing, this number here. Oh, shit.
X.
Yes, so I got my backwards formula. If I know the z-score, which I do, and I know the mean, I know the standard deviation, I can see what my data point is. So to get to my data point, I start at the mean, which was, what was it, 718.3, and I go 2.05 steps. What was it? Oh, crap. 223.5 steps. And that's the definition of z-score. It makes sense. And then you just plug in a calculator. What do you guys get? I get all kinds of stuff.
1,176.59.
Woohoo! So if somebody goes out and tests some people in this little area, and they get levels around that 1180, 1170, 1180, stuff like that. Would you say, from what we've discovered here, is that an unusual amount of rating? Why? Yeah, it's the top 2%. It's more than 2 standard deviations away from the mean. I like it. So I can use this to backwards figure out, well, what's the maximum level, the minimum level. If you get beyond that, I would be concerned. So that would be an area of concern for me if I saw that. I like it. Let's see. Is there a nuclear power plant nearby? What's happening? All right. And this is really the same problem. It's just that where's this going to be? Down here. I like it because it's only got 0.23 below it. So if you look up 0.23, and again, you got to stop. If you start doing this, you got to go, wait a minute, brain. Bless you, bless you. One more? No? 3 means money. That is not a z-score, right? I need to figure out the z-score. So I got to look in here. 0.23. What'd you guys get? Negative 0.74. So z-score negative 0.74. So I don't know the raw score yet. So we use the same formula we just did. 718.3 minus 0.74 times 223.56. So now I start at the mean and I go down this many steps. This is the bottom 23%. Kind of makes sense. And what do you guys get for that?
552.8656.
Can you be more specific? Don't you? Milligrams. I like it. Is that what you guys got? Everybody got that? It's wrong. No, all right. Sorry. Excuse me. I didn't really get that yet. Okay. Any? Yes.
Are you stickler for units when doing this kind of problems? Or we work from z-scores backwards?
Yeah, I mean, I really should put milligrams up here, yes. And the answer should be in the right units, so you don't have to change decimals into percentages, but you can if you want to. But if it's a backwards problem where I ask you for a time level or a time limit or whatever, you should give me units. Yeah.
Can you do a part B one more time?
This year?
Yeah.
So we converted 860 into a z-score. That's just a z-score, so I have to look up the area. And we've got that area. But the problem wants greater than, and the chart tells me less than, so I have to do 1 minus to get that side. Cool. I like it. Yes? E? So, T23, that's the 23rd percentile. So that's the score that has 23% below it. So it definitely can't be above the mean. It's got to be below the mean. So I want to make sure that putting it here makes some sense. Somewhere down there. Cool. Now that tells you the answer is going to be negative, so there's like a check in here. You can make sure you're on the right track. That's an area. So I want to look up the z-score. So I gave us an area, a percentage. You got to look up the z-score, which you can then convert back to an x-score. That's the path I want to take. So if I look up 0.23, the closest I get was here, 2296. And that's a z-score of negative 0.74. And now I use, that's negative 0.74 z-score. Now I can use the formula mu plus z sigma. I can start at the mean and go. Now, if I want to follow the formula directly, it's plus, but then the z-score is negative because I want to go down that many steps, and each step is this big. Plug that in the calculator and you get the 552, whatever. Cool. Is that cool? So that right there needs to not be crazy, intense, or difficult. Right? It isn't. If you think it is, you need to come see me. Because the math isn't that crazy. The ideas actually aren't that crazy. Because now everything kind of builds off of this. So we need a really good foundation for this. So we're going to start to build on it a little bit today. Oh, snap. Oh, so let me ask you some questions to get us going. Dadgum. That's not good. Go away. Somebody fix that. Alright. So we're going to do sort of a rough outline of something because I have a handout here with all of it on it. But it's all already worked out, so I don't want to give it to you yet. I want you to help me work it out a little bit. Alright. So let's say I write the numbers 1, 2, 3, 4 on pieces of paper and put them in a hat. Just because. Right? And what are the probabilities for the possible outcomes? If somebody just reaches in and pulls one out at random and then drops it back in, what are the probabilities? Well, don't overthink it. What's the chances I get a 1? 1 out of 4, 25%. I like it. A 2? 1, 2, 5. 3? 1, 2, 5. 4? I like it. So they're all equally likely because there's nothing, they're all the same piece of paper. There's nothing that would tell me one is one thing or another thing. I don't have such sense of, there's more ink on that one. It must be the number I don't know. Right? Alright. Can you guys, this will be a nice review. take a minute and figure out the mean, which really shouldn't be that hard, and the standard deviation. Figure it out. Do it. Or sit there and look at me. I'll give you a little hint. Just doing this because this will be on our next test. We might as well remember how to do this. I think that's right. No, yes? You guys are looking puzzled? Good? Remember this? So that's the mean, right? When you add this column up, and what do you get when you add that column up? 2.5. Now, hopefully somebody out there realized it's just averaging 1, 2, 3, 4. So of course 2.5 is the average. Now here, the formula for the standard deviation, this is a piece of it. So what do you get when you add these up? Are these the numbers you guys got?
Yeah.
So you get 5, 7.5. So the sum of x squared p of x, that whole thing is 7.5. So I can put that in the formula. Let me stop there for a second. This shouldn't look completely alien unless you are a non-believer in Homer. This should be hopefully familiar looking. Sum of x squared p is 7.5. The mean was 2.5. That's the variance. It's going to be this difference. 7.5 minus 2.5 squared. Is that 1.25? So what's the standard deviation? One point 118. I like it. That's correct. All right, let me stop there. So, kind of makes sense. How far away on average does everything get from the middle? That's half away. That's 1.5 away. That's half away. That's 1.5 away. So on average, about 1.18 away. Let me stop. Okay, so what if instead, and what do we normally do in statistics? We don't normally talk to one person. We normally talk to a group of people, right? So, what we're about to get into, let me let's put this on a back burner for a second. Let me see if you guys are with me, and then we're going to kind of prove this concretely. So I'm going to get a little abstract now, which you should expect from me, and then we're going to get very, very concrete in a minute. This is my favorite problem again. My favorite example is the ages of people in Florida. So this is if I took one person at a time. How would I construct this picture? You guys remember what this was? This is the ages of people in Florida, some alternate dimension in Florida. right? So how would I construct this? I would talk to somebody, I'd say, how old are you? And you'd say, I'm 87. And then, or maybe say, I'm 87. I don't know. However you're feeling at that age. And then I'll put a dot there that represents you, right? And then just keep talking, and the dots pile up for everybody's 87. They pile up a lot for the people that are 60 something. A lot of retirees, right? And they pile up a lot for these people. I mean, you guys, I talk to a person, put a dot. Talk to another person, put a dot. Talk to another person, put a dot. That's one way I can make this kind of picture. Are you guys semi with me? All right. So instead of doing that, let's take 20 people at a time and say what's your ages, and then calculate an average age and then put a dot. So then that'll be a picture of not the ages, that'll be a picture of the sample mean ages. Oh shit, Jeff. So I'll take a sample of size 20 from Florida, random sample of size 20. Say, write your ages down, I calculate an average, and then I put a dot. I take another sample of size 20. Average their ages, put a dot. You guys semi with me? Because this is really good for saying, okay, what's the probability that I pick one person who is more than 60? Then I can find this area and then I'm done. You guys with me? But what if I said, what's the probability I pick a group of 20 people who are older than 60? I can't use this picture because this picture is representing individuals. I need the picture that represents groups of size 20. Then I can compare them. You guys semi with me here. This is a picture that represents individuals because how is it created? Put in a little dot for every single person. So if I want to say, is this group of 20 people, are they unusual or something? I got to compare them to all groups of 20 people, and that's not what that thing does. Damn thing. So it's got a mean. It's got some kind of standard deviation, blah, blah, blah. So if I took a group of 20 people, what is the most likely average that I'm going to get? Let me say this a different way. What would you expect to get for a random group of 20 people from Florida? Like, there's an average age at Grossmont, right? Let's say the average age at Grossmont is 27. If I take a group of 20 people, what would be your best guess about the average age of that group? 27. So if I take a group of 20 people from Florida, the most likely thing to happen is close to this at least, right? In fact, physically, what's the most likely thing to happen? I get a mixture of people from here and there. What's the least likely thing to happen? Well, the least likely is in here because there's nobody, but the least likely that's bigger than 0% chance would be getting a bunch of 90-year-olds, right? Just randomly. I just randomly pick, you, how old are you? 91, you? By the 18th person, I'm like, what is happening? I'm not walking around one area in Florida. I'm taking random groups of 20 people from all of Florida. Are you with me? So if I randomly selected a bunch of Grossmont students and their average age came out, like 20 Grossmont students, and the average age of them came out to be 90, something has probably gone wrong. Right? Is that impossible? No. Is it unlikely? Hell yes. Right? It's like getting 5 Yahtzees of 6 in a row. Do you guys even know Yahtzee anymore? Yahtzee? Is it an app on the phone yet? Yes? All right. What? Shake the phone? Can you shake the phone? That'd be cool. No? All right. So, for n equal to 20, the picture is going to look more like what? Now, the highest bump should be where? Based on what we just said a minute ago. Over the mu. Right? So if I get a bunch of people, a mixture of people from here and there, and I keep plotting the average ages, I should plot the most right here on top of the mu. And then the next highest peak should maybe be around this. So maybe it's going to look like this. Something like that. So you got peaks for these, and then the most likely thing will be a mixture of both, right? A bunch of young people, a bunch of old people. All right, is this making sense so far? This is the abstract part of it. Then we'll get to the nuts and bolts. What changed? And let me write this down. Let me see if you guys are cool with this. What does this represent? What does the dot up there represent? Group of 20 people. Their average age, right? So this is the average of all the sample means, right? It's the mean of the means. So if there's an average age in here, and there is, there has to be, that would be weird if there wasn't. If I take 1% at a time and then average those, would I get a different number than if I took 2 people at a time, average their ages, and then average those? Would it come out to a different number or not? No, it would not. It's the same people, right? Just because I take 2 people and average their age, 2 people average their age, and then I average the averages, it's still going to come out to the average of the class. If I took every possible pair of people, are you guys with me? If I left out nobody. Now obviously I left out some people, all bets are off, right? But I'm talking about everybody. So this picture is every possible group of size 20 represented. Most of them will be right here. Now what's neat, if that's not neat enough, I don't want to erase you. All right. But when you get to, I can just write on top. When you get to like 30 or above, let's say 38, sure. It's going to look like this. So once you get to 30 or above, it becomes normal enough. This is what I just said earlier today. When do I have a situation where I know it's normal enough? When you have a sample size of more than 30. Everything becomes normal enough after. If it starts off normal, it's going to be normal no matter how many people you pick. If it starts off uniform, it's going to get to be normal a lot faster than 30. So 30 is kind of like the extreme. It's like the most. It's like the weirdest distributions become normal enough at around